Welcome to Lecture 2 for Astronomy 20, Astronomical Scales and Classifying the Universe. So in the first lecture, we introduced a number of terms and concepts, spent a little bit of time on scientific notation, and talked about how to try to wrap our minds around the sort of mind-boggling distances and length scales, both large and small, that we will be concerned with during the semester. Today we're going to continue some of that, but we're also going to take a step further and start an initial discussion about classifying the universe, because as we discussed, the study of science in general, whatever the discipline is largely concerned with classifying nature into sort of logical groups and understanding the relationship between those groups. And so that's what we're going to do today. So we're going to start off with something that is going to take up a lot of our time and hopefully interest throughout the semester, which is stars. So let's go ahead and define what it is that a star is. So a star is a huge ball of ionized gas, which is known as a plasma. It's mostly hydrogen and helium, and it generates huge amounts of energy from nuclear fusion. So, and this last part, the nuclear fusion part, is a defining characteristic of a star. So if we think about, and we'll talk at some length about this, what's the difference between the Sun and Jupiter, for example? Because compositionally, they're very, very similar. Almost all hydrogen and helium with little bits of other things. What's so different about them? And the answer is the Sun is a star because it's hot enough in the core for nuclear fusion to occur. And as a result, it generates its own light, whereas Jupiter is not. So a star generates its own light using nuclear fusion, and it's formed of plasma. So, and that last part is important as well. Stars are not made of gas, okay? It's not gas. It's something different, entirely different. It's a different state of matter. It's a plasma. So when you were in middle school, for example, and you were first introduced to the concepts of states of matter, you were probably taught there were 3 states of matter: solid, liquid, and gas. It turns out that was not the end of the story. There is a 4th state of matter called plasma. And we will talk, as we go on, we'll talk a little bit more about what that is. But if you learn nothing else in this class, I want you to walk away at least knowing that stars are made of plasma, not of gas. Okay. Moreover, stars are so hot that the atoms are unstable, and this is essentially, you know, a defining feature of the plasma again. So if you think about moving between the different states of matter and how you would do that, you would start off in a solid, and you would heat it up. You would add energy, and eventually you would give enough energy that you would that the atoms or the molecules in the solid would jiggle around fast enough that they would be able to slide past one another. They wouldn't be locked in position anymore. And that's a process called melting. So that's something you're familiar with. You may not have thought before about what's happening on the microscopic scale, but that's what's happening, is that the atoms in materials are always jiggling around. Even in a solid, the atoms are not totally at rest, but the repulsive forces between the neighboring atoms and molecules are strong enough that they can't move past one another. So they're basically locked in position. But if you heat them up enough, they overcome that, and they do slide past one another. And that's what a liquid is. So if you heat up a solid, you move these atoms faster and faster, and eventually they melt into a liquid. So what happens if you keep heating? Well, if you keep heating, the liquid molecules move faster and faster, and eventually they start to move fast enough that they not only can slide and move past one another, but they can actually escape from each other altogether. The attractive forces between the different molecules and atoms in the liquid are overcome by the energy of the liquid atoms or molecules moving. And that's a process known as boiling. Okay, so another process you're very familiar with. May not have thought about it in this way before. So now you have a gas, okay? Once you've vaporized everything, you've boiled everything off, you now have a gas. What happens if you keep heating it? Well, at first, not a lot. At first, you just heat, the temperature of the gas increases, and you go from from a warm gas to a hot gas to a really hot gas. But eventually, if you give it enough energy, you actually start stripping electrons off of the atomic nuclei. And when you do that, you move into a completely different state of matter, where instead of having atoms flying around in this gaseous phase, you actually have nuclei and electrons, which have been separated, flying around. And it turns out that the properties of that system are very, very different from the properties of any gas. So it really is a new state of matter, and that's what a plasma is. And so you know, to restate it again, there are four phases of matter: solid, liquid, gas, and plasma. And this plasma is created by just pumping gobs and gobs of energy into a gas, heating it up so much that you strip the electrons away from the nuclei. And so instead of having a gas of atoms, you have a gas, if you will, of nuclei, of positive nuclei and negative electrons. But it has very different properties again than a normal gas. And so it really is a new state of matter, and we call it a plasma. So now that we know what a star is, let's define a star cluster. One thing that I will tell you I'll prepare you for, something that you're going to run into throughout the semester. Astronomers, and dare I say scientists generally, are very often not very creative in their naming schemes. And as it turns out, this will actually be beneficial to you. I think it's something that my high school chemistry teacher called the name thing, which is that we're not very creative in our naming schemes, and so very often the name of something tells you a lot about what it is. Now, unfortunately, there are some contradictions as well, or some counterexamples. But if we run into a counterexample, I'll tell you. So a star cluster is a cluster of stars. Okay, it's a large group of stars that importantly is formed from the same gas cloud in interstellar space. So we'll talk in several weeks from now about the process of star formation. But to simplify it a lot and to sort of spoil it a little bit for you in the future, stars form out of clouds of interstellar gas. So there are large, very extended clouds of interstellar gas just out there in space. And over time, due to gravity, those clouds will tend to collapse. The different atoms and molecules in the cloud will be attracted to one another. It will take a long time, but after enough time, those gas clouds will condense. They will start collapsing under gravity, and eventually some parts of those gas clouds will get hot enough and dense enough to start nuclear fusion processes, and that will give rise to the birth of stars. And so in the simplest sort of way that we imagine this, you can imagine just a single star forming out of a cloud of gas. But it turns out that in practice, many stars are formed out of the same cloud of interstellar gas. It doesn't collapse perfectly symmetrically. There are parts that are a little denser than others, and so you form stars in kind of random locations throughout the gas cloud. But because many stars tend to form out of the same cloud of gas, these stars tend to form at very similar times, and they tend to have essentially identical compositions in terms of how much hydrogen, how much helium, and things like that. And so a star cluster is just a cluster of stars that were all formed at about the same time from the same cloud of gas. And these stars, because they formed out of the same cloud, they're relatively close to one another, at least in astronomical terms. And as a result, they're close enough to gravitationally influence one another, and they tend to orbit around a common center of mass. And so you could have, a relatively large number of stars that are kind of all orbiting around one another, and that all have very similar ages. So now that we know what stars and star clusters are, let's talk about the next thing that we think about in astronomy, which is a planet. So what is a planet? It's one of those things that we tend to know in our mind. We have a very clear sense of what it is until somebody asks us, well, what is it? How would you define it? And then we pause and scratch our heads for a while. So in the interest of not pausing and not scratching our heads for too long, I'm going to tell you what we're going to mean when we talk about a planet. So a planet is a body of significant size that has two critical characteristics. One is that it orbits a star, okay? And the second is that it is not a star, okay? And this kind of might go without saying, but we're going to be pedantic, and so we're going to say it. And in particular, by it's not a star, we mean it's not producing its own light, right? It does not have nuclear fusion going on in the core. It's not producing its own light. If any light is coming off of it, it's because it's reflecting off of it, having come first from a star. Okay, so one thing you might be inclined to ask is what is this significant size here? A planet is a body of significant size. Who decides what significant is? Well, that's a great question. And it turns out that people disagree over that, and they've changed their minds throughout history. It's getting, you may have heard about the demotion of Pluto some years ago. When I was in elementary school, even through high school, and I think even college, Pluto was a planet. But shortly after, maybe when I was in college, maybe early grad school, Pluto was demoted, and it's no longer a planet. So it does orbit a star, so it definitely has this. But I guess the powers that be decided that a planet is not, or that Pluto is not of significant size anymore. And there actually are additional attributes that are not going to be important for us particularly, like clearing its orbit. If you really want to look further into it, so we can talk about that if you like. But since this class is one on stars in the universe, we're not actually going to be spending much time at all talking about planets, but it will come up from time to time. So I figured I'd put a slide in here to tell you exactly what it is we're talking about. So a planet orbits a star, and it's not a star. And planets can be rocky or gaseous, right? And we see that certainly in our own solar system. There are, as we have discovered, lots and lots of extrasolar planets, that is to say, planets that are outside our solar system orbiting other stars, and people can and do spend careers studying those. We're not going to talk very much about that at all this semester. We'll touch on it just very briefly. But if you're interested, know that those things are out there. So speaking of which, how do we observe planets? So we know they exist, but how do we observe them? So there are a couple of different ways. In our solar system, they are usually observed by just observing the light that they reflect from the sun. So we've said a planet doesn't generate its own light, right? All it can do is reflect light from somewhere else. And in our solar system, that somewhere else is from the sun. So the sun gives off light, that light hits the planet. Some of that light, not very much of it, but a little bit of that light is reflected back in the direction of Earth, and we can observe that. Obviously, this is easier to observe the closer the planet is to us and the closer the planet is to the sun, right? So Mercury is very close to the sun, so it's going to get relatively a large amount of light from the sun, and it's going to reflect that light, and we're going to have a good chance of seeing it. Venus and Mars, same thing. And those planets are relatively close to us as well, and so their reflected light doesn't have to travel too far before we observe it. Pluto is a whole lot harder to see because it's 40 times as far away from the sun as we are, so the sun has to travel 40 times the Earth's the distance to get to Pluto. It has to reflect off of Pluto, which is only 1/6 the size of Earth. That light then has to travel back 40 times the Earth's orbital radius again, roughly, to get to Earth, and then we observe it. So the amount of light that's left by the time that it goes out to Pluto, gets reflected back, and gets observed on Earth is very, very small. And for that reason, Pluto can't be observed with the naked eye. You have to have a telescope, and even that, you have to really know where to look. Okay, but still, for our solar system, we can observe either with the naked eye or with a telescope. We can observe planets by virtue of the light that they reflect. That's not true for extrasolar planets, right? By which we just mean planets outside our solar system. And there basically are two ways that we can observe those stars. One is by their gravitational influence on other objects, and specifically, this usually means on the star that they're orbiting. So if a planet is orbiting a star, we usually think, and even I just said, the planet orbits the star, right? Strictly speaking, and we'll talk about this in more detail in the next couple of weeks, the star is not actually perfectly still in space. And so we often talk about a planet orbiting a star, but in fact, the star also orbits a little bit, and they both orbit around their center of mass, as it turns out. And so with very precise instruments, very high quality telescopes, we can actually observe the very small movement of the star due to the gravitational influence of the planet. But in order to observe that, the planet needs to be reasonably large. It's obviously going to be smaller than the star, but it needs to be reasonably large. So for example, if you have the sun and Jupiter, we would be able to observe the influence of Jupiter on the sun. But if you have Pluto and Jupiter, or Pluto and the sun rather, we would not be able to see that effect. So for relatively large star or planets, and or planets that are relatively close to their stars, we can see a slight gravitational influence. But for those that we can't observe that, there's a second way that we can observe extrasolar planets, and that's by the light that by noticing the light they obscure when they pass in front of the star. So if you look at the figure here on the left, Kepler 4b, for example, which is just an example of an extrasolar planet, it's hard to see because it's just a little black dot there, but there is a black dot. This planet is going to orbit. When the planet is behind the star or to the sides of the star, you're going to see it's not going to block any of the star's light, right? The star is going to emit light in all directions. Some of that light is going to make its way to Earth, and we can capture that light in a telescope, and we can figure out how intense is that light, how much light is getting to us. But when the planet passes in front of the star, it will block a little bit of that light. And so the intensity of the light reaching Earth will actually drop just a little bit. And much to the credit of the experimentalists and the technicians that develop these high quality telescopes, we can actually observe and measure in detail that the decrease in the intensity of the light. And so you can see what's being plotted here basically is the intensity of the light as a function of time. And so you see just this little dip, and so the intensity drops while that star is orbiting in front of, or when the planet is orbiting, passing in front of the star. When it passes beyond the star again, then the intensity comes back up. How big that dip is, unsurprisingly, is a function of how big the planet is. So if you look at Kepler 5b, it's a noticeably larger planet. It makes a much bigger difference, a much bigger dip in the intensity of the light block. And so all you need is a really powerful telescope that you're not going to just buy off the shelf, in case you were wondering. But if you have a powerful enough telescope that can do the job, you can actually observe the intensity patterns in this way, and thereby infer, even though you can't actually see, if you just look at the star, you'll never see the black dot, but you can observe the effect of the light that it blocked. So another thing that's worth saying at the outset, because I'm going to refer to this over and over again, is that one cool aspect of astronomy is that it gives us effectively a way to look back in time. Okay? And the key to understanding this, and the reason this is true, is that light does not travel instantaneously. It doesn't travel infinitely quickly. It travels very quickly, but at a finite speed. And if you're wondering exactly what that is, it's very close to 3 × 10⁸ meters per second, or about 300,000 kilometers per second. So that's really fast. In day-to-day life, we usually we don't think about it. When I turn a light switch on, as far as I can tell, the light immediately comes out unless the bulb is burned out. But it turns out it actually does take a split second for that light to travel from the bulb to my eye. And while it doesn't make a difference on Earth, when we're viewing things billions and billions of miles away, it turns out that it does make a difference. And in particular, the farther away an object is, the longer it takes its light to reach Earth, right? It's similar to, if you've ever, I grew up in Indiana where we had thunderstorms regularly this time of year. So one of the things that we would often do is when you heard thunder or when you saw lightning, you would start counting and ask and figure out how many seconds did it take until you heard the thunder. And then you would divide that by 5, and that would tell you how many miles away the storm was. And the reason is that the light got to you essentially immediately, and whereas sound traveled much slower than the light, and so you were essentially using the speed of sound to figure out how far away is the storm. Well, it turns out that you can do the same thing with light on astronomical scales. And so if an object is 10 billion light years away, for example, it's going to take 10 billion years for that light to get to us. And so if I look up in the sky and I see something that's 10 billion light years away, I know that I'm seeing it 10 billion years ago. Now, unfortunately, there's no way to speed it up. So it's cool that I get to look back in time there, but the thing is so far away that I know that even if there's a star 10 billion light years away, if it explodes today, I won't know for 10 billion years. And of course, then I just won't know because I certainly won't be around, looking up at the sky in 10 billion years. What's cool about the universe is that there are some parts of it that are close and some parts that are farther away. And so if we look at something close, we are looking at a part of the universe more or less today or in the very recent past. Whereas if we look at something very far away, we're looking at the universe much farther back in its history. And so this is going to be important because when we talk about stellar evolution and how stars form and evolve and then eventually die, the reason that we're able to know those things is that we can look at stars which are being born and stars which are in the middle of their lives and stars that are dying in different parts of the universe. The whole process takes much too long for us to observe. Even the shortest lived stars live on the order of 1 million years, and most live much, much longer. So we would never be able to observe that in our lifetime. But by looking at lots of different stars, which are at different places in their life cycle, we can piece the picture together. So it's kind of cool, and it's important to keep in mind that we're always looking back in time when we look at the sky. But you don't quite know how long you're looking back in time or how far back in time unless you know how far away you're looking. So another effect that we need to be aware of when we think about looking at the stars is that how bright a star looks depends intrinsically, very, very significantly, on how far that star is away. Right? And so all other things being equal, dimmer stars are usually farther away. And that's just because when a star or anything else, a light bulb like in this image, when a star emits energy, it emits energy equally in all directions. These stars are very nearly spherical. They just emit light in all directions. And as a result, if you think about the energy emitted in 1 second by the star, well, it emits a certain amount of energy. And then that amount of energy as it travels out, it gets spread out over larger and larger areas, which means the intensity of that light gets lower and lower and lower. Okay? And we'll come back and we'll talk more about this. But for the present purposes, this means that if all stars emitted the same power, which is just energy per second, so if every star in the universe were the same size, same temperature, emitted the same energy per second, then if we saw a bright star, that would mean, aha, that star is pretty close. Okay? And if you saw a dim star, you'd say, okay, that means the star is relatively far away. And that would be it. But as you might imagine, it turns out that that's a big if, and it's not true. Okay? So all other things being equal, dimmer stars are usually farther away, but not always. So how do we observe these stars, right? I mentioned in the very first slide in lecture 1, I made this audacious claim that astronomy is the oldest science. And the reason that I made that claim is that all it takes is walking outside after sunset and looking up, right? And now you're an astronomer. And for a long time, that's all we had. And actually, one thing that we'll see is that it really is just remarkable how much people were able to learn and discover with just using the naked eye and keeping meticulous records and being smart, it turns out. So there was a whole lot of progress that was made before the invention of the telescope, for example. But as you can imagine, the invention of the telescope made a huge difference in terms of our ability to collect data and make observations and discoveries that were just impossible before. So the telescope was first developed in 1610 by Galileo. It's worth saying that Galileo seems to have been the first person to take a telescope, what we would call a telescope, and point it at the sky, which is kind of what a telescope is, right? But he did not develop the technology. Okay, the technology for that is a telescope, which is essentially a couple of lenses that enlarge an image, was developed in 1608 by a few different people very much at the same time. So there's actually a bit of a disagreement about who should properly be given credit. In any case, it was not Galileo, and it was developed for seafaring folk, for ships, because it turns out it was nice to be able to see a little bit farther out and see if there was a ship coming or if land was coming and things like that. But Galileo had the good sense to take this technology recently developed and point it up at the sky, and astronomy has never been the same since. But as you can see, we've come a long way. So this is kind of a Galilean telescope developed in 1610, and then you go 380 years down the road, and you get the Hubble Space Telescope, which looks a little bit different, and the Keck telescopes as well. So there are all sorts of different kinds of telescopes: ground-based scopes, space-based scopes, ones that look at light in the visible spectrum, some that use radio waves or X-rays, and we'll talk in some detail about that. But telescopes, even in Galileo's time, but certainly today, they collect more light than the human eye, and in some cases a whole lot more. And so they do two different things that are related. One is they collect more light than the human eye can do, and two is that they can look at a lot of different. They can collect just a lot more data that way. And as I mentioned, anytime we look at the sky, we're looking back in time. But telescopes allow us to look farther back in time because they allow us to see things that we just can't see with the naked eye. So having mentioned the Hubble Space Telescope, here's a nice about 10-minute video introduction to the Hubble Space Telescope, which was launched in 1990, as I said. So for what it's worth, I was 7 years old at the time, and I remember this was a very exciting time in the area. I remember being excited about it too, with my 7-year-old astronomy magazine. But it was expected to live on the order of 10 years or so and return data for 10, maybe 20 years. It turns out that it's still going strong. It's had some issues, but fortunately we've been able to repair it several times, and it continues to give us just sort of amazing quality data and observations of things from very nearly the beginning of the universe. And so, as I mentioned a couple of times, we're looking back in time when we look at the stars, and so the farther away you look, the farther back in time you're looking. And the Hubble, which is a space telescope, so it's outside the Earth's atmosphere, which allows it to avoid the negative influence that the atmosphere has on astronomical observations. It also has the largest aperture, which we'll talk about more, but basically the largest opening for collecting light of any space telescope currently deployed. And so it's given us unparalleled quality images and insight. And so I certainly encourage you to watch this 10-minute video. I won't play it myself in the middle of my narrations because that would just be a waste of time. But watch the video and then continue.
Incredible.
So, astronomical sizes. We've talked a little bit already about some of the relevant sizes in astronomy, but it turns out that there are a lot of objects we're going to be interested in, and so we're going to hit a few more here. So, we've talked already that the sun is much larger than the Earth. And certainly if it's much larger than the Earth, it's much larger than the moon. To give you some concrete numbers, the diameter of the Earth is about 13,000 kilometers, diameter of the moon about 3,500, and the sun is 15 million kilometers. So, you know, to compare those things, the sun's diameter is more than 100 times bigger than the Earth, 109 to be precise, but we often just round that to 100. And the Earth's diameter is roughly 4 times that of the moon. To give another comparison here, kind of a scale model, as we talked about in the last lecture, we've got the sun, the Earth, and the moon here. So the distance from the sun to the Earth is about 400 times the distance of the moon to the Earth, and the sun is about 400 times wider, larger in diameter than the moon. And so here again are some concrete numbers. So if you like comparing things, there you go. And these are pictures that we saw again in the first lecture, but you know, throw back up here for good measure. The moon's diameter is almost, not quite the distance, you know, coast to coast in the continental U.S. And the distance between the Earth and the moon is about 100 times the size of the moon. So again, you could stack 100 moons side to side, and that would, you know, just about get you from the Earth to the moon. So something that I mentioned earlier, but we'll be a little more concrete about it again now, is that the nearest star to the sun, which means the nearest star to Earth other than the sun, is known as Proxima Centauri, which happens to be part of a triple star system named Alpha Centauri. So go back just a few decades ago, before our telescopes got the resolution that they have now, which always continues to improve, you would have learned that Alpha Centauri was the nearest star to the sun. Since then, we've been able to discover that, in fact, there are multiple stars that are orbiting around their common center of mass that we're able to distinguish now. And so over time, in fact, which one of, you know, the closest star will actually change, because at some point Proxima Centauri will orbit away from the sun, and Alpha Centauri A or B will orbit closer. But for the time being, during our lifetimes, this will remain the case that the nearest star to us is Proxima Centauri, and it's approximately 4.3 light years from the sun. So, you know, I've mentioned several times now that you're always looking back in time. When you look at the sky, when you see Alpha Centauri, you're looking back 4.3 years, which is the closest thing that we can observe outside our solar system. So let's talk now. I told you we're going to be classifying the universe, so let's talk about some of that classification. So we know what the solar system is. It's not something that we're going to focus on a lot in this class, because the focus of Astronomy 20 is stars in the universe. If you're really interested in the solar system, I encourage you to take a look at Astronomy 10, which is the solar system. But the Earth is part of the solar system, and we kind of know what that is. If we zoom way out, then the solar system lives inside the Milky Way galaxy, and the Milky Way consists, like most galaxies, of hundreds of billions of stars. So, you know, unimaginable number of stars, essentially, that happen to be set up in a pretty pattern, looks like a spiral. But that's our galaxy. If you continue to zoom out, we discover that there actually are several galaxies that are in the same sort of area in space. And by that, I mean they're close enough to one another to influence each other gravitationally. And so, and we call that, not creatively again, our local group. So the local group is just a set of approximately 50 galaxies. And I say approximately because different people will count them slightly differently, in the sense that there are things known as dwarf galaxies, which are kind of like they sound, not like real galaxies, but just smaller. And so some people will say, well, that's a dwarf galaxy, and others will say, no, that's just a small galaxy. And so I've seen numbers as low as 30 galaxies in our local group, and I've seen numbers as high as 50. So the precise number is not important. What is important is just to know that there are multiple galaxies that are relatively close to each other in a relative sense, and that attract each other gravitationally. And then if you zoom out farther, you get to something which is known as the Laniakea supercluster, which consists of just an egregious number of galaxies and is enormous. Okay. One caveat is that if you had taken this class even, I think, 15 years ago, you would have been told that after the local group, there was something called the Virgo supercluster, and that was the supercluster that our local group exists in. Since then, the definition of a supercluster has been reworked, much like, so I mentioned in the last lecture that Pluto used to be a planet and got demoted and is now officially no longer a planet. Well, the Virgo supercluster used to be a supercluster, and now it is no longer considered one. And so our supercluster is now the Laniakea supercluster. But to further add to confusion, for historical reasons, people continue to refer to the Virgo supercluster as the Virgo supercluster, or sometimes, if they're a little more detail-oriented, the Virgo local supercluster. So the Virgo local supercluster is inside, it's part of the Laniakea supercluster, and so we're in both of those. So it might have been a little bit clearer if I added in here, another picture here of the Virgo local supercluster, where, it would be clear that we're part of the local group, which is then part of the Virgo local supercluster, which is part of the Laniakea supercluster. These are names, and obviously the physics and the astronomy, the actual science doesn't change as we change these classification schemes. But unfortunately, it is important to keep up with the times as best we can there, just so that we have a way of communicating with other people in the field. For us, since we're not going to be going to any astronomy conventions as a class, so the important thing for us is just to remember this, so that I can say that I've taught you what I was supposed to teach you, and so that you can do well on the homeworks, quizzes, and exams. So the Milky Way, it's a great candy bar, and it's our galaxy. And we'll talk in quite a bit of detail about the Milky Way in a month and a half or two. But for now, since we're focusing on classifying the universe, kind of focusing first on our local environment and then getting bigger, there are a couple of things that we do want to sort of cover at the outset. The first is the Milky Way is a spiral galaxy, and if you want to be a little more specific, it's a barred spiral galaxy, and that's just because if you look closely here near the center, you can kind of see a relatively thin but noticeable bar that cuts across the center of the galaxy. Some spiral galaxies have that bar, others don't. Ours has a relatively thin one, but it's there, so we're a barred spiral galaxy. And the Milky Way consists of hundreds of millions of stars. Okay. It's also 100,000 light years across. So we happen to live about halfway out to the edge in one of the arms. And again, we'll talk about that in more detail going forward. But one advantage of being out kind of in one of the arms is that we get a pretty cool view if you can get out far enough away from city lights and so on, which is really not that easy depending upon where you live in the Bay Area. But near Livermore, for example, if you get down to Del Val Park and get far enough out, you probably lose cell coverage, but you'll get some great views. And so, for example, you can actually see this is a side-on view of the Milky Way from inside the Milky Way, right? So again, we'll talk in more detail about that, but in terms of classifying the universe, the Milky Way is our galaxy, and these are a couple of really high-level attributes that we should be aware of. So zooming out even farther to our local group, the local group consists of roughly 50 galaxies. So as I mentioned a couple of slides ago, some sources will say closer to 30, and the reason they will say that is that they'll take 20 of these galaxies and say, well, those aren't real galaxies, those are dwarf galaxies. You know, it doesn't change the reality, right? The galaxy or the dwarf galaxy doesn't care or know, you know, what we call it. And so as a result, the precise number isn't important here either. But it is important to know that most of the galaxies in the local group are these dwarf galaxies, or you know, which just means that they're smaller, quite a bit smaller than the Milky Way. So you know, the Milky Way is by no means the largest galaxy in the universe, or even in our local group, but it is on the larger side of things, and so most of them are smaller. This is actually something that we're going to see throughout the semester, is that it's more common to find smaller things than bigger things. So, for example, the most common element in the universe is hydrogen, which is the smallest. It's more common to find small stars than big stars. It's more common to find small galaxies than big galaxies. And so we're going to find that throughout. And frankly, it makes sense because it's easier to form a lot of small things than one big thing. And we'll revisit that, but I just want to kind of throw it out there for the moment. So this is kind of an image or a schematic of our local galactic group. It's obviously, you know, we obviously can't take a real picture of it because there's no way to get a camera out far enough away to take a picture like this. And you're certainly not, we're not going to be studying the details of any of these other local galaxies. There's only one that, or maybe a couple that we'll talk about in any detail at all. And so when we do, I'll tell you. But so certainly don't try to memorize this image or anything like that. But it kind of gives you some sense of scale of what, you know, the Milky Way is here. It's hard to read, but Milky Way is written in red there. So that's us. You can see we're one of the brighter, one of the larger galaxies there, but not quite the largest, which looks to be Andromeda over here, which is one that we'll revisit. So the Milky Way, if you zoom in there, again, here's a nice, pretty picture of the top view, if you will, of the barred spiral. Again, not a real image, at least not of the Milky Way, because we can't get an image like this of the Milky Way because we're stuck inside it. But this is very much what it would look like. If you go to our nearest neighbors within the local group, it turns out they are known as the Large and Small Magellanic Clouds. They get their name from the fact that they were observed by Magellan's crew when they were out in the ocean, away from even the lights that existed then, and they are dwarf galaxies. You know, I've mentioned a couple of times we're not very creative in our naming schemes. They're large and small because they are large and small. If you go to get a little bit bigger and ask, well, what's the nearest small galaxy? So it's not like a very small thing like the Magellanic Clouds. Sagittarius is the nearest small galaxy, and it's about 75,000 light years away. Andromeda, which I mentioned, is the nearest large galaxy, and it's about 2 million light years away. So our local group, if you zoom out yet again, belongs to the Laniakea supercluster. And as I mentioned, this was defined very recently, so just back in 2014, less than a decade old. And so, you know, prior to that, I would have, if you'd taken this class, I or whoever was my predecessor would have told you that the Milky Way belongs to the local group, which belongs to the Virgo supercluster. But the Virgo supercluster got demoted. It's no longer a supercluster, and so we are now in the Laniakea supercluster. And so much to my chagrin, and I think to most people, the definitions in astronomy are, you know, it might be an overstatement to say they're constantly evolving, but they do evolve. I think, you know, the only people that like these evolutions are the people that come up with these new definitions. which I assume they do just because they can't do any, sort of make any real discoveries or do any real work, and so they just, confound everyone else that's trying to do real work. But it's something that we need to be aware of anyway. Okay, so this is just for fun. I'm throwing this in here because, again, we're talking about classifications, and so we're kind of, some of these things are connected more than others, but quasars are something that are just a really cool, exotic thing that's out there in the universe that hopefully we'll have some time at the end of the semester to come back to and talk in a little bit more detail about. But these are really cool because they are among the brightest, most energetic objects in the universe. They're just, it's really hard, I keep saying this, but it's really hard to wrap your mind around how bright these things are compared to anything else that we experience. They tend to be located at the centers of galaxies, and they can emit thousands of times more energy than the entire Milky Way, every second. So, the Milky Way is 100 billion stars or thereabouts, right? So we're talking about a single object in the center of a galaxy that can emit hundreds of thousands of times more energy than those hundreds of billions of stars that are in the Milky Way, which is, it's just mind-boggling. And for what it's worth, they were most common about 10 billion years ago. And if it sounds weird that we know that, remember, we're looking back in time when we look out in the cosmos. And so when we look out in the sky and look for quasars, and of course in the beginning we didn't look for them, we just found them and we're like, wow, that thing is really bright. Why, how on earth can that happen? It turns out that most quasars are very far away. So we figure out how far away is this. We find, on average, or they were most common, 10 billion light years away, which means, well, they emitted their light 10 billion years ago. And the reason that I mention that is that there's a lot of ongoing research now into quasars, and in the early days after their discovery, there was a lot of question as to what are these things? I mean, how were they formed? What are they made of? How on earth can they emit this kind of energy? And so the fact that they were most common 10 billion years ago is an important data point because it gives you some sense, though it's not immediately obvious what that tells you. Whatever it tells you, as you're thinking about how did these things form, what it means is that they formed much nearer the beginning of the universe than we are today, right? The universe today we estimate to be around 13.7 billion years old. We'll talk about that in more detail much later in the semester as well, because there are a number of caveats that should be made to that estimate. But assuming that that's right, quasars were common, in the relatively early universe, not in the very, very early, but much earlier than we are today. And so the question is, well, why would that be? How can we use that information to help us understand how these things might have formed? It turns out that, in the very recent past, I mean, during my lifetime, certainly, there's been a lot of development and understanding of quasars, and we now understand, or at least are pretty confident we understand, that quasars are really generated, it's light that's generated by swirling gas as it falls into what's known as a supermassive black hole. Yet another example of a very uncreative name, but we'll talk about black holes later in the semester, but it turns out that almost every galaxy that we observe now, and possibly everyone, appears to have a very, very massive black hole in its center. And by very, very massive, we mean hundreds of thousands to millions or more solar masses. So think about taking millions of suns and then forming a black hole out of them. And it turns, so the gravitational field created by these things is just unimaginably strong. And so it kind of swallows everything that it can, thus the name black hole. And so as this gas that's getting, in the neighborhood of these supermassive black holes gets swallowed up by it, it starts traveling very, very quickly as it falls in because of the gravitational forces. And so it heats up and it swirls around and it emits huge amounts of light. And so here we have it. This is an artist's rendering of it because it turns out that we can't get a really fancy picture of a supermassive black hole. But but this kind of gives you an idea of what it would look like if you could get there. So we do now have a pretty good idea about what quasars are, but they continue to be a very fascinating area of modern research. And as I said, hopefully we'll have some time to talk about them in more detail later in the semester. So let's say a little bit now about the stuff of interstellar space. And as I've said several times now, and makes sense since we're in the introductory part of the class, almost everything that we're talking about now we'll talk about in more detail in the weeks and months to come. But interstellar space is, as the name suggests, just the space between the stars. And it's almost, though not entirely, completely empty. Okay, so it's, I've said it a few times now, there's a lot of emptiness out there. Interstellar space is mostly empty. To tell you how empty it is, on average, there's about 1 atom per cubic meter. Okay, so to kind of compare that to something else, if you have a piece of stuff, any stuff in your hand, a cubic centimeter of a milliliter of water, for example, or something like that, that tends to have about 6 times 10 to the 23 particles in it. Avogadro's number for any of those that have taken chemistry. That's like 6 with 23 zeros after it. Okay, in a cubic centimeter, maybe. In contrast, we're talking about 1 atom per cubic meter. Okay, out in interstellar space. So almost nothing. Right? Not quite nothing, but almost nothing. What is that something? It's mostly hydrogen. I mentioned that it's much easier to form small stuff than large stuff, and so we tend to have a lot more small stuff in the universe. Hydrogen is the smallest element, lightest element, and the vast majority of what you find in interstellar space is hydrogen. You'll also find a little bit of helium, and then you'll find small amounts of interstellar, what we call dust. Which it's much, much smaller than the dust that that you have to clean off your dresser every Saturday morning or whenever it is that you do your cleaning. But it's much larger than the hydrogen and the helium atoms, which are the common things out there. And it tends to be made of these heavier elements like carbon, silicon, and oxygen. And then I should say that there's possibly, apparently, lots of questions surrounding something else mysterious that you may have heard of even just out in pop culture news, which is called dark matter. And this is something that we know very little about. We will talk about it in some detail, at least as much detail as we can in a few months from now as we get near the end of the semester. But dark matter is stuff that's dark in the sense that we can't see it. We've never seen what this stuff is. That's why lots of people speculate about what it's made of. But we infer its existence from its gravitational effects. So to make a long story short, we look at how the Milky Way and how other galaxies rotate and evolve and move and things like that. And you can calculate, okay, well, how much mass must there be in order for gravity to have these effects? And when you compare that calculation to the amount of stuff that you see, you find out that you're missing quite a bit. And so the conclusion that one draws is, well, there must be some other mass that we just don't see, doesn't emit light, doesn't scatter light, and just kind of sits there invisible to our electromagnetic, sort of observations. And so they call it dark matter. And so, as I said, we'll talk more in detail about that, but this is the stuff of interstellar space. It's mostly empty. We have a few kinds of atoms that we know about, and then there seems to be this dark matter that we understand very little about, but I'll say more about going forward. So, again, just in terms of classification, we call this dark matter dark because we can't see it. It doesn't emit and it doesn't interact with light. But we know, or we think we know that it's there based upon gravitational effects. I'll come back to this again when we talk about dark matter in detail, but But it's important to keep in mind that the reason we think dark matter exists is that we do calculations, and our calculations don't match the observations. But those calculations use a theory of gravity, in particular Einstein's theory of general relativity, which seems to work very well in many cases, but again, seems to predict that there must be this dark matter. So it's possible that there's this dark matter that we just haven't figured out what it is yet. It's also possible there's a problem with general relativity. So again, we'll come back to that. We'll talk about it. But there's dark matter is one of those areas of modern research that there's a lot of work still being done and a lot more unknown, I would say, than there is known. One thing that is known, and one reason that dark matter is widely believed to exist, is that its gravitational pull can actually bend light. And this is a consequence of general, or it's described by Einstein's theory of general relativity. And so this is a famous image where you see this ring here. It's obscured, blocked by a cloud of gas here, but you see an almost complete ring of light here. And what's actually happening is that there is a source of light very far back along this line. So if you follow the red dot really far back, there's some source of light emitting lots of light in all directions, and it's being bent around a large mass that's in here. And it's massive enough to bend light. The light is bent back, and it arrives on Earth in this ring. And so it looks like there's a ring of stuff, but it's really just the same object's light being bent around. So it's emitted, comes out, gets bent back, and then observed as a ring. And so it's a very powerful thing. There's no question. You can analyze the light in this ring, and there's no question that it's all coming from the same source. So there's not a ring of matter emitting light out here. There's a point of light essentially that's emitting, a point source emitting this light that then is being bent around by a huge amount of matter, because it takes a lot of mass to bend light. And so you can actually calculate, well, how much mass must there be? And then again, you compare that to the amount of mass that would produce the amount of light that you actually see, and you find out there's this missing mass, and that's the dark matter. So I kind of apologize for going through that so quickly. We will talk about dark matter in quite a bit more detail in the months to come. Right now, I just kind of want to put the term out there, make clear that it's mysterious. There's a lot unknown about it. But when you're thinking about what's the stuff that's in interstellar space, dark matter seems to be an important piece. So there's another, and this is what we're going to wrap up with here, is this claim that we are made of stardust. Okay, so we've talked about what's in interstellar space. We've talked about what, in fact, the first slide was stars, and I told you then that stars are made up mostly of hydrogen, and then a fair amount of helium as well. By number, we'll come back to this, later. I keep saying that, but we will. But it's about 90% hydrogen by number. So if you counted the atom, the nuclei in a star, you would find, or in the universe, you would find that about 90% of them are hydrogen. Almost all the rest are helium, and then you have just small amounts of the others. But essentially, what happened is that the universe starts with hydrogen. The first nuclei that form are hydrogen nuclei. And then as they form stars, those stars, through the nuclear fusion processes in their core, produce the heavier elements. And so the stars themselves are responsible for transforming the hydrogen that they start with into heavier elements. First helium, then carbon, oxygen, and all the way up to iron. And when I say all the way, I mean in terms of the periodic table. So a few slides back, there was an image of the periodic table, and you can certainly Google and find one as well. But as you walk your way up the periodic table, you can form heavier and heavier elements in stars until you get to iron. And it turns out that the nuclear fusion in the cores of stars will not go past iron. And there are reasons for that, interesting physics reasons for that, that we'll talk about when we discuss stars in detail near the middle of the class. But it turns out that when stars die, in particular when when very massive stars die, they can generate what are called supernovae, which is just a fancy way of saying the star explodes. And in that explosion process, it turns out that stars are capable of producing much heavier elements, all the way up to uranium, and even heavier. But the heavier ones are radioactive enough that those things will decay away and they won't be observed later. But so the light elements, everything up to iron, can be produced in stars under normal circumstances. The heavier elements between iron and say uranium are produced, as best we know, only in these supernova explosions. And then these supernovae, which are some of the most energetic things in the universe, explode and fling all of these heavier elements that have been formed off into space. And it takes a while, but the universe has been around for a while for that material to move out into space and spread out throughout the universe. And as far as we know, all heavy elements in the universe, including all of the stuff, all of the metal, heavy metals, think uranium, tungsten, and anything above iron on the periodic table that we mine for, that we find in the Earth, as far as we know, all of that came from supernova explosions, according to the astronomical theory. And remarkably enough, the theoretical predictions that allow you to calculate, well, how much iron would you expect, how much tungsten would you expect, how much tantalum would you expect, and so on, match up quite well with observations in the universe. So there's a lot more research that continues to go on in that field. But when you hear me or someone else say we're made of stardust, this is the sense in which we mean it, is that our current understanding of the physics processes in stars and in the universe is that all of these heavier elements are made either through the fusion in normal stellar activity or in special processes, nuclear processes that take place during supernova explosion. So with that, that brings us to the end of lecture 2. So I appreciate your attention. If you have any questions, as always, feel free to post to the course website or contact me, and I will see you back for lecture 3.